Okay, so previous lecture we defined how to work out convective and diffusive fluxes and we looked at temperature diffusion and also momentum diffusion. And in real life, if we want to actually calculate the flow field, we've got to define these things everywhere in the domain. So we took a 1D problem for energy and we derived the equation, and this lecture we're going to do three things. The first one is have a look at the temperature profile in our problem to understand the balance between convection and diffusion, and then we're going to look at a way in which we non-dimensionalize the equation and take out the key scales of the problem and derive some non-dimensional numbers, and we as engineers use these to work out what's going on in our problem before we do any calculations. And this is a key skill for us as engineers. And then the final thing that we're going to look at is we're going to look at the non-dimensional force momentum equation, which you've already had a look at. So we're going to look at it in a slightly different way. We're going to non-dimensionalize it, and I'm going to try and explain why we are going to separate momentum problems into inviscid and viscous problems for the remainder of this module. Okay, so if you remember previous lecture, we derived this equation, and we said it's for this problem here. So it's a 1D flow in a channel, and the upstream side is low temperature, and the flow comes from the left hand side, goes towards the right hand side, and at the right hand side we have a high temperature. So physically what's happening here is convection is blowing cold fluid into the domain and from left to right, and diffusion is spreading hot fluid from the right to the left. And so the temperature profile in the middle of this domain between x equals 0 and x equals 1 will be a function of the relative strength of the convective and diffusive flow of energy. And we did this applying a control volume, and we said, well, we know what's going on in the middle of the control volume, and we did the Taylor series to extrapolate the information to the faces, and then we said, well, we need to work out what the convective and the diffusive fluxes are on these faces, and then we said it's a steady flow, and there's no energy creation inside the control volume. Therefore, conservation of energy tells us that the fluxes going in and out of the control volume for energy must balance, and we made that statement, and this is the equation that must hold given to define conservation of energy in this particular control volume due to the convective and diffusive fluxes. So the left hand side we have a convective term, which is a function of U. On the right hand side we have a diffusive term, and that's a function of the thermal conductivity and the temperature gradient. Okay, so we want to look at what does this equation tell us when we set effectively U and K. Okay, so trying to make this a little bit simpler, we can say we've got a material constant C, and it's a function of the thermal conductivity and the density and the specific heat. So this C is just a physical constant that changes whenever you change the fluid. Okay, and just to make this problem super simple, we are interested in the temperature profile between x equals 0 and x equals 1, and rather than use T equals 275, I'm going to say x equals 0, T equals 0. So T equals 0 is cold, and T equals 1, which is at x equals 1, I'm going to say that's hot. Okay, so temperature goes between 0 and 1, which is cold to hot. And we've got two tunable constants in here. One is U, which if you make U bigger, you're going to have more convection, and you've got C, which is effectively your diffusion constant, and if you make C bigger, your diffusion is going to be stronger. So we can play around with U and C, and we can play around with the temperature profile. So let's look at what this little toy gives us. So what we've got here, these are my boundary conditions. So T at 1, so the x-axis is on the bottom, so we've got x equals 0 here and x equals 1 over here, and what we're saying is temperature x equals 1, so that's this point here. So my y-axis is temperature, and the temperature at 0 is equal to 0, so that's fixing my temperature here. So these are my two boundary conditions that I need to solve my problem. And then I say, well, I'm going to say my velocity is 10 meters a second, and my diffusion kind of constant is 1, and I get a temperature profile that looks like this. Okay, so this is the temperature profile ensuring energy conservation, given that a certain amount of convective flux is coming into this control volume from this side, and a certain amount of diffusive energy is coming in from this side. And if we think about the diffusive flux is a function of the gradient. So the gradient's reasonably steep here, so there's some diffusion going on here, but more or less it's a convection. Well, it's a fairly balanced problem, but there's a bit more convection than there is diffusion, because there's more cold fluid in the domain than there is hot fluid. So we can increase the convective strength by making U bigger, and we do this on the next slide. So here we look and we see that we've made the convective power or flow of energy much stronger. So in this case you can see that almost all of the fluid in the domain that we're interested in between x equals 0 and x equals 1 is effectively the temperature of the fluid at the convective boundary, so this one here. And there's only a tiny bit of diffusion in the domain, but that diffusion is actually quite strong because this gradient is really sharp. Okay, but it just can't penetrate very much into the fluid because the convective strength of the energy transport is so strong. And then the flip side is, if we take our velocity back down to 10, we make our diffusion coefficient 5 times bigger, we then see that it becomes very much a diffusion dominated problem. So there's a lot more hot fluid in this domain, and the convective flow can't really push the cold fluid into the domain here, and the convective and the diffusive power is such that we would call this a sort of a diffusion dominated problem. Okay, so this is what we can do to understand the problem, but this is quite complicated. It takes a lot of steps. We've got to derive the equation, we've got to apply boundary conditions, we've got to solve the equation, and then we can find out what's going on. It would be much easier if we could work out what was going on without having to do all these steps. Okay, so that's what this next part of the lecture is all about. So what we do is we take a variable, which is something like thermal conductivity, and we separate it into something that a variable that kind of it varies in the domain, but it varies. The important thing is the value of this is of the order 10 to the 0, so somewhere between 0.1 and 10, say, and we have a reference value. And these reference values, we are the big and the small numbers. And we collect these together, and we use these to work out what's going on in our fluid. So the process is really trying to work out what the relevant scales are in the problem. Okay, and effectively what we're saying is we've got a variable, and we try and find the key thing that defines what this is. Okay, so in this particular problem, for physical properties, we've got 3 that we're interested in. We've got the thermal conductivity, we've got the specific heat, and we've got the density. And there are some more that we can use in other problems. So as an example, let's say we've got a domain where the viscosity varies in it. So this might be due to temperature variations. Okay, so let's say our viscosity varies from 0.5 times 10 to the minus 3 to 3.2 times 10 to the minus 5 Newton seconds per meter squared. Okay, so that in our domain our viscosity varies over this. So what we do is we take a reference scale to be 10 to the minus 5, and then our normalized or variable is just a variation on this. So in this particular case, my u star mu star varies from 0.5 to 3, and we can always recover the real variable by taking our reference scale and multiplying it by the variability. Okay, so this mu star, this is constant, doesn't vary in the domain, and this is how the variable varies relative to this, and we can recover the real viscosity using this equation. Okay, and the key point to remember is that this term, the reference scale, holds all the dimensions, and this thing is dimensionless, and we try and make it about 1, more or less. And we also apply this to the length and time scales and the variable of interest. So in this particular problem, our variable of interest is temperature. In the example that I've used, effectively I've already non-dimensionalized it, so my T0 is effectively 1. But let's say I was running the problem and the temperature varied from, say, 280 Kelvin to 300 Kelvin. I might say then that my T0 was 300 Kelvin, and my T star varies a little bit about 1. Okay, so in this particular problem, so when we're defining the geometry and the velocity scales, we have 3 choices. We've got the length variable, the velocity variable, and the time variable. And so only 2 of these are independent. So if it's a steady flow, we're not actually interested in the time. So we say our time scale is a function of the velocity and the length scale. And that's what we're going to do here. So the only 2 things we're interested in here is effectively these 2 and the temperature. We also have to take a reference scale out of our space and time operators. So these are the d by dt and d by dx. So in this particular case, we only have to worry about the spatial operator. Okay, and so we can non-dimensionalize the spatial operator by saying, well, my definition for x star, my non-dimensional length, is x divided by x0, and I can differentiate this in the same way that I might have y equals x, and therefore dy by dx is 1. So in this case, dx star by dx is 1 over x0, and remember, x0 is a constant, so it doesn't vary in space, and so I can rearrange this little equation to have a relationship between my dimensional d by dx term and my non-dimensional d by dx star term. And so here my 1 over x naught is my kind of scale. Okay, so once we've got all of these, we can start to put this into our governing equation and non-dimensionalize it. So let's look at the left-hand side here. We've got this term here, and we want to non-dimensionalize this, and we do this by substituting in the reference and the reference scale and the non-dimensional variability. So let's take u, and u is equal to u naught multiplied by u star. Okay, so I take this variable and then I say, well, that's equal to u star and u0. So here's my u naught and here's my u star. And then I do the same for t. I say, well, t is equal to t0 times t star. And then I say that t0 is a reference scale and it doesn't depend on x. So I can take my t0 out of my differential operator and I can put it here. And my t star is effectively my my variability as a function of x, so that has to stay inside my differential operator. And then I've got my d by dx, and I can substitute that for 1 over x0 d by dx star. So here's that's why my x0 appears here, and here's my d by dx star here. Okay, and I can do exactly the same on the right hand side. I'm not going to go through that here. Okay, so then we get to here, and then what I do is I say, well, I want to divide both sides of my equation by u0 t0 divided by x0. So I end up with this equation here. So it's worth having a quick pause here and thinking about what we've got here. So remember that I took u0 and made it into I took u and made it into u0 u star, such that all my starred quantities are going to be about 1. So what that means is this term, whatever I do, however big or small the problem is, this thing on the left hand side is about 1. And the same for this reference scale over here. This is about 1. And the things that I'm pretty sure are definitely not 1, in fact all the big and small numbers in the problem, they are all the subscript 0 terms here. Okay, so that's what we've got here. So I know that this is going to be about 1, and I know that this is going to be about 1, and I know that this is definitely not going to be about 1. The other interesting thing about the equation is, if you remember, the u stars and the t stars and the d by dx stars, they have no dimensions. So this term has no dimensions, and this term has no dimensions. So because this is the only term on the left hand side, this must be a dimensionless equation. Okay, and that also means that these variables here, so these c0 and u0 and x0, these all have dimensions. So u0 is in meters per second and x0 is in meters, and so on. But it means that if this entire equation is non-dimensional, the thing in the square brackets must be a non-dimensional group. So that's quite interesting. We've come across non-dimensional groups before. So this group of variables is a variable called the Peclet number, and the Peclet number is a variable that defines the relative strength of convection to diffusion. So let's think about what we've got here in this equation and what we can work out from this equation. So if the Peclet number is really, really big, it's much, much bigger than 1, it means that it means effectively that this term on the right hand side is much, much smaller than this term on the left hand side. And this term on the left hand side we know is about 1, and we know that this dashed term on the right hand side is also about 1. So if this thing, if the Peclet number is much, much bigger than 1, then this term in general is much smaller than this one, and so it's a convection dominated problem. On the other hand, if the Peclet number is much, much smaller than 1, then this term over here is much, much bigger than this term over here, and it's a diffusion dominated problem. And if we know if it's a convection or a diffusion dominated problem, we can make a reasonable estimate of what the temperature profile is between the two boundaries, and we can kind of understand what's going on in the problem without having to derive everything and solve the equation and apply boundary conditions and all that kind of thing. So this is quite powerful, and this is what engineers do when they first see a problem. They take the scales, they work out the relevant non-dimensional numbers, and then they make a comment about what's important and what's not, and how you can simplify the problem and solve it and still get a reasonably good answer. Okay, and we can do a little bit more with the Peclet number. So that's what the Peclet number is, which we got from above here, up here, and we can put in what C0 actually was. If you remember from earlier on, it's the thermal conductivity divided by the density divided by the specific heat. And then what we can do is we can say, well, we can multiply and divide by viscosity here. So here's viscosity on the top and here's viscosity on the bottom, and we can group these things together in slightly different ways. And then we can recognize that this is 1 over the Reynolds number, and this is a new one that we haven't come across yet called the Prantl number. And so we can write the Peclet number as the product of the Reynolds number times the Prantl number. Okay, and so we can start understanding what's going on by understanding what these non-dimensional numbers mean. And this is a much better way of working out how to map physical effects onto these non-dimensional numbers, much better than using the Buckingham pi theorem. So these are the kind of non-dimensional numbers that we're interested in on this module. We know about the Reynolds number. We've got the Prantl number. So this is the ratio of the viscous diffusion flux, if you like, and the thermal diffusion flux. And you can see when you multiply the Reynolds number and the Prantl number together, the viscous fluxes cancel, and you end up with the convective flux of energy divided by the thermal flux of energy. And that's what our Peclet number gives us. And we've come across the Froude number before. This is body forces over inertial forces. We haven't come across the Mach number, but this defines effectively when we have supersonic flow, when the flow speed is faster than the speed of sound, or the wave speed. Okay, so the final bit of this lecture, we're going to spend a few minutes just talking about non-dimensional momentum conservation. So this is not part of the module, but I want to include it to make you understand how we make the module simple enough to deal with in part 1. So we can take our momentum equation, and it's called the Navier-Stokes equation, and we can apply exactly the same non-dimensional procedure that we did for the 1D convection diffusion energy problem, and we end up with an equation that looks a bit like this. So these i's and j's are tensor notation, and they just tell us that something with an I or a j is a vector, and if you've got an I and a j, it means it's a tensor. But don't worry about this, it's not important. What I want you to understand is the Navier-Stokes equation fundamentally has 3 terms that are of interest. We've got a convective term, so this is the convection of momentum, in the same way that we did convection of energy. And this term over here, this is your viscous term. So this term handles your viscous diffusion of momentum, and we talked about how that works in a previous lecture. And we've got a force due to the pressure gradient of the fluid. So this is quite unique to force momentum problems. And it's really, so the richness of the Navier-Stokes equation comes about because you've got convective momentum, you've got pressure gradients, and you've got viscous forces. And in general, all of these things are going on at the same time. Okay, and the key point for this module is we don't do everything at once. We do special cases, and I'm going to try and explain how we do that. And the other reason why the Navier-Stokes equations are interesting is this term is nonlinear, and it's this nonlinear term that gives us our richness of fluid mechanics and turbulence and chaotic solutions. Okay, and this term is big when the Reynolds number is very large. Okay, so and the viscous forces can't stabilize the flow. Okay, so this is an example of the flow past the cylinder at different Reynolds numbers. So this is the Reynolds number where it's really small, this is a medium Reynolds number, and this is high Reynolds number. Okay, so in this photo, the viscous forces are relatively very strong compared to the inertial forces or the convective forces. So the flow is very stable, and the solution to the Navier-Stokes equations gives this kind of flow pattern. In the opposite extreme here, the convective forces are much stronger than viscous forces, and the viscous forces can't stabilize the flow. You generate all of this instability and chaos and turbulence. Okay, so because the Navier-Stokes equations are a nonlinear equation, you can get completely different solutions purely by changing the Reynolds number from the same equation. Okay, so this is one of the interesting things about fluid mechanics. Makes it a good research area and generates lots of problems that are very hard to solve. So how do we handle this in part 1 thermofluids? So this is really the object of this end of the lecture. So here's my non-dimensional Navier-Stokes equation, my general case. And effectively what we do in part 1 is we take we take limiting cases, and we don't do it all at once. So the first one is we say that my Reynolds number is huge, and therefore my viscous forces are negligible. And if I do that, effectively I put a 0 through this term, and my Navier-Stokes equations become a bit simpler, and they're called the Euler equations, and effectively they are a balance between the convective flux of momentum and the pressure gradient. And we've already come across this at the end of last term, and we deal with this not in a differential form but an integral form, and this is the type of equation that you've come across before, and hopefully you can appreciate that this is very similar to this. Okay, so we're going to do a bit more work in this in the next few lectures. And then what we do is we say, well, my Reynolds number is tiny, it's much less than 1, so this term is much bigger than these other two. And when we do that, effectively we're solving this equation, and this equation is called the Stokes equations, and it's useful in things like lubrication flows, so the flow of oil around bearings, and applications such as that. And we consider this equation as a basis for all of the viscous flow problems that we look at within the last five lectures of this term. Okay, and the one we end up solving is a 1D form of this, which is actually this. Okay, so I've sort of set this up not because I want you to do anything with this rather unpleasant and very complicated equation, but because I want you to understand the simplifications we're making in part 1. So we're looking at all of the richness of the Navier-Stokes equations, but we're doing it in the limiting cases and not doing everything at once. You'll be doing everything at once in part 3, part 4 of your degree. Okay, so we've looked at, we understand what 1D convection diffusion problems look like for energy. We've worked out how to non-dimensionalize them, come up with some non-dimensional numbers. We get an idea of what the Reynolds number does and how it affects the character of the flow. And I've introduced the Navier-Stokes equation, which we're not going to deal with in its full form in this problem, but we are going to deal with simpler forms at limiting cases of Reynolds number. Okay.